Hi, everyone. Thank you for joining us for Universal Scalable Firmware, Security Aspects of an Evolutionary Approach to System Firmware. We'll get started here in just a moment. Thank you. Hey, everyone. Thanks again for joining us for Universal Scalable Firmware, Security Aspects of an Evolutionary Approach to System Firmware webinar as part of the UEFI 2023 Virtual Plugfest. We wanted to take a moment here to introduce our presenters. So we have Jiewen Yao, who's a principal engineer in the Intel Software and Advanced Technology Group. And then we have Vincent Zimmer, who is a senior principal engineer in the Intel Software and Advanced Technology Group. Additionally, I wanted to flag that we will be moving to a WebEx Q&A following this webinar meeting. And so this will be a chance for you to chat live with the presenters and ask any questions you may have. And with that, I'll pass it off to the presenters.
Hey, thank you. So yeah, today we want to give you a guided tour of an effort we call Universal Scalable Firmware. Give you a brief overview of what the effort entails, and then dive deeply into some of the security dimensions, including hardening, work underway for updating OpenSSL, and then some of the background and effort toward compliance with upcoming security algorithms. So this will be our tour. I'll be the cruise director for the beginning, and then I'll hand off to Jiewen for the rest of the deck. So what is USF? So USF is actually a initiative that covers sort of a full stack view of host firmware. The next slide will show a diagram, but I'll give a quick summary here of what it is and where to find more information. It essentially speaks to interfaces from the top of your firmware stack, sort of the OS loader facing interfaces, and the encapsulation mechanism there. We'll talk about as something called a universal payload, and then how that universal payload can compose with various host firmware infrastructure, whether it be EDKII, core boot, slim boot. You can imagine, inducting on this with, U-boot or boot, but infrastructure, common infrastructure, potentially across all these different, essentially platform construction frameworks, and then how to talk to silicon underneath. And there's be a quick touch on that. And again, for the full stack, USF talks about infrastructure, coding guidelines, and presently it's guided by a GitHub community, github.com, Universal Scalable Firmware, and a groups.io, so you can wander over to the GitHub and see what's happening, and roll with the groups.io community meetings. Some of them have been journaled on YouTube. And then what's inside USF, the public-facing aspect, has a specification, and that's compiled to this location, but it's in sort of markdown style format. So you can see the history, give feedback, open GitHub issues, create pull requests. And then for kind of an overview of all the layers of it, there's a talk at OSFC in 2021 if you're interested in not just staring at a specification, some YouTube videos of meetings. You can catch an overview presentation. So that's what USF is in a nutshell. It's really raise the the quality, some of the interoperability, how to do firmware. But one of the most important firmware, and the venue why we asked to come here is UEFI style firmware, whether it's the UEFI specification or PI, and implementation substrates like EDKII are critically important. So what we thought we would do today is, in order to frame, sort of give some context about what USF means in practice, we're going to deep dive into where USF touches UEFI, and specifically where it touches EDKII infrastructure and security considerations. So if you open up the main USF specification, you'll find a security section. So as I noted before, it's kind of a full stack architecture. How we attempt to get reuse at the top, replaceable payloads with a well-defined interface. How we construct and can get reuse across the platform, various platform implementations, something we call the POL, and then an FSP style interface to talk to silicon. But security is really, again, the aspect we're going to talk about, and largely the, again, UEFI style code, EDK code. And to that end, if you click one more layer into USF and security, you'll see some guidance on, hey, if you're building this host firmware, there's some considerations you should keep in mind, whether it be around protection, detection, recovery, cryptographic considerations, and then mitigation guidelines. So again, belief here is that if you have host firmware, some of these security concerns are almost a common good. How do you achieve assurance? What's some guidance to that end? And this is where the USF specification reads in. It has, again, some, goes from some abstract to some concrete guidance. And later in the talk, you'll see specific discussion on how some of this guidance reads on EDK style firmware. So again, back to the top, USF, full stack. How do we get reuse of code through payloads? How do we get more interoperability and reuse at the platform layer? And then how can we abstract out silicon at the bottom such that we can then explore opportunities like perhaps defragmenting the supply chain? So again, since we're sort of doing this peekaboo, drive-by view of USF, we elected to, talk about one aspect of the initiative that reads on, a topic you've seen earlier. We talked about the supply chain earlier, firmware bills of material. So one of the things USF is vying to do is, as it goes to that 3-layer cake of generic boot technology code at the top, abstracted through payloads, fit to purpose platform code in the middle, and then silicon specific code at the bottom. This is an opportunity to say, wow, EDKII, UEFI, rich, powerful specifications, several thousand pages, a million lines of code, but a lot of the code is very common idioms, right? File system drivers, consoles, your sort of Dixie core / kernel. Is there value in everyone fragmenting and having different variants? Perhaps if we're purporting to do EFI, we can have a single instance of that generic code that's largely technology specific, platform independent. And this is one way to do it would be to fabricate it as this payload. Generic platform independent code, parameterized through data from that POL layer underneath. And why would you do this? Well, now you can maybe, as a community, have some well-known artifacts. Say, hey, if I'm doing UEFI 2.10, this payload is conformant to that. And then those 12 CVEs you might have seen landed in the last couple quarters have been addressed in part by this code. So you can sort of snap it in. And then if you're a slim bootloader, core boot, or an EDK native platform code, get the same reuse. The supply chain can have a manifest, just as we talked about publishing the FSP manifest as one well-known binary object. Here's yet another well-known binary object, so that the supply chain can potentially introspect and detect whether they have, quote, the latest code, whether it's from a feature perspective or assurance, i.e. it's fixed certain bugs. And so this is one, again, as USF is attempting to increase the quality of the firmware ecosystem, this is one aspect of it, and then how it reads on security, and in fact reads on a discussion we've had in this forum before. So that's kind of a treetop, USF, full stack, open community specification, abstracting generic code at the top through payloads, platform code built through largely open source frameworks in the middle, and silicon vendor code at the bottom. And then how that top layer reads on security, namely reuse and more traceability of this critically important code for the UEFI ecosystem. But the journey doesn't end there. And in fact, assurance and construction conceits across the whole stack are critically important, specifically EDKII code. And so I'm going to hand off to Jiewen, and he's going to walk us through the other portions of the USF security chapter and crypto assurance, and some thoughts on how we might go forward with the community. So hand it off to you, Jiewen.
Okay, thank you, Vincent, for providing the introduction of the USF. You know that the security of a USF firmware is more than measurement, and the table shows here all aspects of the security assurance. Basically, we have 4 tactics. First, we should try to eliminate the possible vulnerabilities. Reducing attack surface is the best way. For example, we know that the SMI handler is a big attack surface in the OS runtime. As such, we should try to reduce the SMI handler as much as possible. Also, the unneeded feature should be removed. For example, the private authenticated variable is defined in UEFI specification. However, we do not see any use case requires this feature in EDKII at this moment. Maybe we can consider remove that feature. Also, we should adopt the firmware security best practice. In EDKII, we publish a set of security documents, including the secure guide, secure design guide, secure coding guide, and the code review guide, etc. Also, Open Compute project published a secure firmware development best practice. So those best practice provide some guidance for the firmware development. Second, if the vulnerability is there, we should consider breaking the exploitation possible. For example, the modern CPU supports a page attribute setting. We can mark a code page to be read-only and data page to be non-executable to prevent code injection attack. And a modern compiler can inject a stack cookie in function parlock and check the same value in epilock. And this is supported by the Visual Studio and GCC to prevent a stack overflow. CPU hardware is adding feature to provide control flow guard. For example, the Intel CPU adds the CET support named the shadow stack and the indirect branch tracking. ARM CPU has a similar feature called point authenticated code, PAC, and the branch target identification. Finally, the address space layout randomization is another feature which can raise the bar for attack. The location of stack, heap, or an image code can be randomized. As such, the attacker it's hard to find the location of this space and put some attack codes there. Third, just in case we fail to break exploitation, and we should consider to contain the damage. For example, the third-party option ROM can be deprivileged to ring 3. Also, the OEM SMN code can be deprivileged to ring 3 as well. So even if the SMN code is compromised, so it can still not impact the OS runtime. Last, we should limit the attack window. For example, with live patching for the runtime component is one way. The firmware vulnerability scan is another way to ensure the firmware does not have known vulnerability. Recently, we talked several times on firmware manifest or bill of material. As such, the verifier can compare the reference measurement with the runtime measurement or the reproducible binaries. Now let's focus more on the second category, breaking the exploitation. So those are possible hardening work we can do in EDKII to support the data execution prevention DP and the arbitrary code guard. We can add we have added the feature to the SMN core and DXE core, including the image protection, non-executable memory protection. So those are enabled in SMN directly, disabled in DXE by default. UEFI 2.10 also introduced a memory attribute protocol, which can be used by the OS loader. And also the SMN code access check can ensure that the SMN code only runs inside of SMRAM. Non-pointer protection is to mark the 0 page to be not present, just in case some code accesses the non-pointer, then the exception can be signaled. The address space randomization can be implemented in 2 ways. First, the data buffer shifting. It means to shift the heap to several pages in every boot. For example, 1 to 16 pages for DXE core heap. As such, the rest of the data buffer allocation will also shift to several pages. The benefit is that the solution is simple. You just need a one-time shift, and when the heap is allocated. One known disadvantage is for S4 resume memory, such as runtime memory, ACPI memory, and reserve memory, etc. Those locations must be fixed and cannot be randomized. And another disadvantage of ASS is for the resource-constrained environment, such as SMM memory. Shifting different memory location may cause a memory allocation failure in some corner cases. The second idea is image shuffling. We know that the DXE core and SMN core need to load image into memory before execution. In current implementation, the order of image loading is deterministic with fixed memory location. With fixed memory allocation, the location of the image code can be predicted. The image shuffling means to make order of image loading is non-deterministic in a different boot. The benefit is this approach is that no extra memory is needed. So all the images loaded in the fixed firmware volume and the allocated space for the firmware volume. The disadvantage is that the order of image start might be different in a different boot. It might fail in some corner case. We also prototyped the buffer overflow detection, such as heap guard, stack cookie, and to detect the heap overflow and stack overflow, or the address sanitizer feature introduced in LLVM compiler. All those can be enabled in debug build, but enable the heap guard in a release image may cause a performance downgrade. Might not be the best idea. Compiler also provides some runtime check, such as undefined behavior sanitizer to detect the typecast error, or memory sanitizer to detect uninitialized access, which is supported by View Studio or LLVM. Last is control flow guard. Both Intel and ARM CPU support those features. CET shadow stack and ARM pack provide the backward control flow guard, and the CET IBT and ARM BTI can support the forward control flow guard. It is good to know that we can do those hardening in the UEFI BIOS. Beyond that, we hope to let end user knows that hardening is implemented there to provide some level of confidence. The problem is that the UEFI or PI ACPI spec interface specification. Now, how do we let the end user knows that the hardening work is available on the existing BIOS? Currently, the industry implemented several ways to report the security hardening capabilities. For example, the Windows SMM Security Mitigation Table (WSMT) allows the system firmware to confirm to the operating system that certain security best practices has been implemented in SMM, such as secure SMM communication buffer. Windows Hardware Security Test Interface (HSTI) specifies a standard test interface for properties of the platform security technologies that enforce the secure boot promise. For example, the firmware code must be present in the protected storage, and the firmware implements a secure firmware update process, and the firmware provides boot integrity check. Also, the DMA protection is available. And enabled. Last, the TCG Platform Firmware Integrity Manifest specifies that the platform firmware assertions can be reported in the platform certificate. For example, the hardware SRTM Secure Boot, SP801-47 Secure Boot, Secure Update, SP801-93 Firmware Resilience, also firmware setup, authentication, SMM protection, and the kernel DMA protection, etc. With those, one possible approach we think is to create a platform integrity mitigation table. We call it PRMT. This PRMT specifies the mitigation applies to the system firmware. So each feature can be reported with an individual bit. For example, the DEP code protection, DEP non-executable data, non-pointer, ASLR, buffer shift, image shift, or control flow guard, backward or forward, etc. And this table could be ACPI table or grid UEFI system table. We feel that ACPI might be a better option since ACPI is the most common interface across all platform implementations, including the Slim Boot, Core Boot, and EDKII. Now let's move to the crypto support. So the EDKII defined a crypto package and a set of crypto library API to abstract the crypto functionalities. Those are important to provide the security features such as secure boot, secure firmware update, trusted boot, H2ES boot, etc. So the current implementation is based upon OpenSSL 1.1. However, this OpenSSL 1.1 will be end of life on September this year. As such, we need to find a replacement. One natural replacement is OpenSSL 3.0. So the OpenSSL 3.0 introduced new APIs and also provide the compatibility mode for the existing 1.1 API. And this figure shows this OpenSSL 3.0 design. The 3.0 split the code into core and a provider. The core is a component in libcrypto that enables applications to access the algorithm implementation offered by the provider. Provider is a unit that provides one or more algorithm implementations. It includes default provider, which implements a set of default algorithms. Legacy provider provides the implementation of old algorithms that will be exposed via EVP level APIs. Eventually, third party may provide their own provider, which implements a set of algorithms which will be accessible to the application and other provider via core. For more details of OpenSSL 3, please refer to that URL. Much detailed explanation on that. Good from Red Hat did a prototype for OpenSSL 3.0 and submitted the initial patch. With legacy mode enabled, we don't need to modify the existing base crypto library, so everything can work as is. It's a really good option. However, the problem is that the size is increased dramatically. The size almost doubled. So if we update it directly, the existing platforms will be broken easily. So what should we do to handle this case? One way is to find a smaller crypto library. So the embedded TS is a non-good choice using the embedded system. It includes a crypto primitive X59 certificate passing and the TRS capabilities. So I did the prototype for embedded TS version 2 in crypto package. The result shows the crypto library is much smaller. However, the downside of embedded TS is that it does not have all features supported. For example, it does not have SHA-3 parallel hash support and SMX, etc. At the same time, we also evaluate other candidates. Here we list all of them. The first one is the Intel IPP. It's an Intel provided crypto primitive. The problem is that it is only primitive. It does not have X59 certificate passing or TRS support. This IPP may be used for ISA-based verification only. For example, the Slimboot project is using that. However, it cannot be used for advanced feature such as the UEFI Secure Boot, which require PKS7, and HTTPS boot, which require the TRS. The second one is libsodium. It is also a crypto primitive only, missing X59 support and the TRS. And the third one is boring SSL. It's a fork of OpenSSL that is designed to meet the Google's need. However, though the boring SSL is an open source project, it is not intended for general use as OpenSSL is. Google mentioned that we don't recommend the third party depend on it. Doing so is likely to be frustrating because there's no guarantees of API or ABI stability. The fourth one is Wolf SSL. It's also a non-good embedded crypto and TRS for device and IoT, and it's got FIPS 140 certificate. The only downside of Wolf SSL is that about the license. It is GPL, which is not suitable for EDKII project. The last one is Bear SSL. It's another crypto and TRS implementation. It is small, both in RAM and the code footprint. However, it's just a beta quality software according to the web page. Based upon that analysis, we finally determined to choose OpenSSL and embedded TRS for further prototyping. We created the OpenSSL 1.1 EOL branch in EDKII staging and post-development work there. We mark some progress on size reduction. For example, the PI size is reduced from 100% increase to 300% increase, which is good now. The DXE and SMS size is reduced from 70% increase to 10% increase. And this data is much better, but not good enough. So we're still working on that. And I also want to thank Gerd Hoffman to provide initial POC. Lee worked on the OpenSSL 3.0 size reduction and submit initial staging. And Art also mentioned that he will provide the ARM stuff if needed. On the other hand, we are working on embedded TS 3.0. So we switch from the embedded TS from version 2 to version 3 because version 3 includes PKS7, which is required by the UEFI Secure Boot. The SHA-3 is still under development. We cared about SHA-3 because we rely on the parallel hash to improve the performance of digital signature verification. Here is a POC result for embedded TS 3.0. The PI size and DXE size is almost reduced to half. A weird thing is that the size of library in PI pre-memory phase, the embedded TS version is larger if only hash is needed. So we will do more investigation to figure out why this is happening. And I'd like to thank Wenxin who worked on the embedded TS3 implementation and submit to staging. Also, Marvin provided the information for the PKSS7 stuff. While we keep improving, we need to consider the plan for OpenSSL 1.0 Q3 EUL because there's a feature missing in embedded TS. The ideal solution is to figure out a way to reduce the size of OpenSSL 3.0 to make it fit into this existing firmware. We realize that the 10% increase is still big, might be a problem for some platform. As such, we consider Plan B. We call it dual mode. That means the EDKII can support both OpenSSL 3 and embedded TS with the two library instances, and the platform can choose the library and the feature based upon its need. So we will see the final result. And last topic we would like to discuss is crypto agility. So NSA published the commercial national security algorithm 1.0 for the existing crypto algorithm. The minimum requirement is RSA 3K and ECDSA P384. UEFI 2.9 and the previous version only support RSA 2K. As such, we added the crypto agility in UEFI 2.10. The main idea is to add the new algorithm with compatibility consideration. So we need to consider the old BIOS boot to a new OS or the new BIOS boot to old OS. To support the compatibility, define the three variables for firmware OS algorithm exchange. The crypto indications allow the OS to request the algorithm to the BIOS. The crypto indication supported allows the firmware to report the supported algorithm to OS, and the crypto indication activated allows the firmware to report the activated currently in use crypto algorithms. The expected flow is that during boot, the BIOS report is supported capability and the activated currently in use algorithm. The OS may choose a subset of the supported algorithm and tell BIOS to use that setting and reboot the system. In the next boot, the BIOS will apply the OS setting and report the new activated algorithm. Beyond that, NSA also provides CNSA 2.0 guideline, which include the post-quantum crypto algorithm. The crypto agility should consider the PQC as well. And this figure shows the CNSA 2.0 timeline. The secure boot and the secure firmware update feature are related to the first category. We need to consider the PQC image signature verification since 2025 and finish the transition between 2030. The HTTPS boot is related to the second category. We consider the PQTLS since 2025 and finish before 2033. We have discussed the UEFI impact on the PQC before, and that is before the final NIST algorithm announcement. But currently, the guideline is more solid since the NIST announced the final selected algorithm, and NSA pick up the subset and provide the timeline. For the industrial perspective, we are seeing the PQC implementation as well. In our previous webinar, we introduced the Open Quantum Safe project, and recently OQS project supported OpenSSL 3.0 with the OQS provider. Assuming we do not need a PQC immediately, that can be considered after the OpenSSL 1.1 replacement. The PQC for embedded TLS is also on their roadmap according to the public information. With that, we can consider the CNSA 2.0 compliance for the UEFI BIOS as well. For example, the firmware image signing or verification can use XMSS or MMS. The general signing verification algorithm is Delicium, and general key exchange is Kyber. The industry is worried about the PQ-TLS because the attacker may archive the current TLS packet and decrypt that with a PQ machine later. So in our UEFI BIOS, we use HTTPS to support the HTTPS boot and redfish configuration. If the main use case is for integrity protection, then we don't need to worry that too much. But if the use case requires confidentiality, such as a password, then the PQTS should be considered earlier, because the decrypting the archived TLS package will expose those secrets. And another thing we need to consider is which digital signature algorithm we should eventually use. And currently, you can have a stateful hash-based signature like XMSS or MS, or general-purpose digital signature such as Delicium. The next guideline is that the image signing could be XMSS or MS. That is under assumption that the released image signing will not happen frequently. But the auth variable might be a little tricky. Using Delicium might be a better way. And finally, we summarize the asymmetric crypto algorithm used in the BIOS. We can see that the main use case is image digital signature verification, including UEFI secure boot, PI signed firmware volume or section, the signed capsule update, signed recovery, etc. Also, the architecture-specific solutions such as boot guard or platform firmware resilience. And we can use PQ hash-based signature in this category. Data signing verification is used in UEFI secure boot, but mainly for the signature database update in a UEFI authenticated variable use case. Since we are going to add the device authentication, I list SPDM-based authentication and measurement collection here. Different from image verification, the device authentication requires general purpose digital signature because we want to verify the freshness of this digital signature. The last category is the secure session establishment, including SPDM secure session for potential PCR link encryption, or the TLS secure session for HTTPS use case. For all those features, we need to prepare the crypto agility and the PQC support for the CNSA compliance in the future. So it's on that, and here is our talk today. So please let us know if you have any questions from that.
Thanks, Jiewen. Thanks, Vincent. The first question that we received is OpenSSL 3.1 is out. Is there a size improvement with 3.0?
So we haven't evaluated the 3.1 yet. So our current evaluation result is 3.0.8. So we are planning to move to 3.1 to see if there's any improvement.
Great. The next question, there's an interest in keeping boring SSL working with EDKII since it's in use in computer engine VMs. Is there a chance we can revisit this? At least as an optional build mode.
Of course, it's a Google project. So Diana, you are from Google. If you can help to evaluate some of them, that would be great. Just a concern about the comments in the web page that says this. Please do not depend on it, and that is our only concern. So if you think that could be used, I'm more than happy to try it.
Great. And so that was the last question that we received coming through the chat. And so I think from here, we can go ahead and move to the WebEx Q&A in case anybody would like to speak with Jiewen or Vincent directly. Here's the information if you all would like to join us. We'll be moving to there right after this. And again, we wanted to thank you all so much for joining the UEFI 2023 virtual PlugFest presentation. The slides will be available on the UEFI Forum website, as well as a video recording here on Bright Talks and on YouTube. Thank you all.